In this video, we're going to talk about rare events and how to write conclusions for a hypothesis tests. So we're still not going to run the full hypothesis test. We're still kind of diving into what it is and how to work it out. And we're going to use this idea of a rare event. So when an event is rare, we actually can kind of get something from that. A rare event happening starts to raise red flags. All right. It's possible. It is possible that a rare event can occur, but because it's rare, you should be skeptical when it does. All right. Let me give you an example. So, right here, a teacher walks into a classroom with a paper bag and states that it's full half with red M&Ms and half with green M&Ms. The teacher says that each student is going to draw out an M&M, and for every student who draws a green M&M, they will receive 5 bonus points. After 10 students, no one has yet pulled out a green M&M, and everyone started to suspect the bag wasn't filled with half green M&Ms. Are they right in their suspicion? So, I mean, this is an excellent example. And I would say that students would probably be way more suspicious than 10. Like after about 5 people, they're going to be like, "Hey, are there really green M&Ms in there?" Okay? And they're going to start to wonder. But really, let's calculate the odds that this could happen. Let's just say for the moment, just to kind of give some numbers, that it's filled with 100 M&Ms. Okay? There's 50 red, 50 green. Just trying to give us some easy numbers to work with. Let's calculate the probability of this little scenario here. So this first student who grabs out an M&M, all right. So here we're going to find the probability that they 10 red in a row. Okay. That means that there are 50 red M&Ms out of 100. And then the second student goes in and they pull out an M&M. Now there's one less M&M in the bag, right? And if there happens to be 49 red left, that'll be out of 99. And then there would be 48 out of 98 and 47 out of 97 and so forth. Okay. So I'm going to finish writing this and I'm going to go ahead and tell you what I got when I calculated because I sure did plug this into the calculator. 92, 41, and 91. And wait, let's see. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I may have actually done my calculation a little bit off because I think I included the next one, 40 over 90. All right, so when I plugged this in, I ended up getting 0.0003. So I'm going to go ahead and adjust and say that I shouldn't have included 40 over 90. Let me see what that gives me. Okay, so instead it's 0.006. All right, that's the odds that 10 people draw an M&M and there really is half of them are green, okay? And they each just keep drawing red, 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 red. All right. Um, those are very low odds, less than 1%, okay? Less than 1% chance that that's going to happen. So the answer is they should be suspicious. I do think the teacher is not being honest. When the probability is this low, we start to suspect that something is wrong. And the thing we should start to suspect is wrong is the initial statement we took to be true. So such a low probability means that it is more likely the teacher lied. And maybe they were trying to make a point that if you can use probability, that means that you've just experienced an event that's so rare that probably means that they did lie in the beginning, just to see if you understand that it was wrong, that what they said was incorrect. So we call this an unusual event. And we say that an unusual event is something that is a less than 5% chance of occurring. All right. So when something is that unusual, we make claims about it that it might not be accurate. Something might be wrong in our initial assumptions. All right. So the initial assumption that we had 50 red and 50 green just might be wrong. I mean, maybe it's more like 70-30. Okay. Maybe they do have some green, but it really isn't half. Okay, So let's talk about how we're going to actually prove hypothesis tests. We're going to use something called p-value. So the p-value is the probability that if the null hypothesis is true, that when we take a sample, we look at the results obtained from the sample. It's the probability that our sample will occur, given that the null hypothesis is true. So when the probability is big enough, we don't worry. We think, okay, that's reasonable that our sample occurred and it had a decent probability that it occurred. But when we take our sample and it has a low probability of occurring, we start to suspect that maybe something is wrong. And in particular, the null hypothesis is what we're thinking might be wrong. So this is how we'll make those statements. We'll look at the evidence from the sample and decide if, based on our sample, that the null hypothesis should be rejected. Okay. So often we want to draw a graph. It does help. In particular, when we draw the null and alternative hypothesis, we kind of have built-in graphs back from 9.1 where we talked about two-tailed, left-tailed, right-tailed. That kind of feeds into this information here. Okay, so let's look at this example here. And we're going to write the null and alternative hypothesis and kind of talk about it. So a baker claims that his bread height is more than 15 centimeters on average. Several of his customers do not believe him. To persuade them, he decides to do a hypothesis test. He bakes 10 loaves of bread, and then he measured all of them, and the mean height from that sample was 17 centimeters. So that means there was actually some that was over 17 centimeters if it averaged out to 17, okay? And he happens to know from all of the bread he makes that his standard deviation of height is about 0.5 centimeters. Okay. And we're going to assume it's normally distributed because we are only working with the normal distribution. So, real quick, I want to state some of the information they gave us. They gave us that the sample was 17 centimeters. And we happen to know that the population standard deviation is 0.5. That's important because all of the hypothesis tests we're going to do uses the population standard deviation. There's a different type of hypothesis test when you're working with a sample standard deviation. Okay, so let's do the null and alternative hypothesis now. So the null hypothesis is we're always going to use the equals. And oops, in this case, we are talking about a mean. So since he's saying it's bigger than 15 centimeters, we'll just say that the null hypothesis is that it's equal to 15 centimeters. And the alternative is that it's bigger than 15 centimeters. I don't really need to write the centimeters on there. In fact, I'll go ahead and get rid of it because it's really not necessary. It's the number we're most interested in. Okay, so we know that the population standard deviation is 0.05. So I'm going to draw a little picture here real quick to kind of talk about this. And since he had a sample, oh, by the way, the sample size was 10. Should have wrote that down. Okay. That means we need to have an adjusted standard deviation. So we need to adjust our standard deviation based on the sample. So our new standard deviation needs to be 0.5 divided by the square root of 10. And that's going to come out to 0.16. Okay, so the mean right here in the middle, that's 15. And the standard deviation is 0.16. Well, the mean of 17 centimeters, that is going to be to the right of the mean. So it's like over here somewhere, but it's going to be like way the hell far away. Okay. I mean, in the normal scenario, the standard deviation is 0.5 centimeters. Okay. And that's well over, that's like 4 standard deviations away from the mean. But because we're adjusting it, since we're talking about a sample, that means then that our data value is very far away from the mean. In fact, it seems almost silly that I'm drawing it this close. I feel like I should be drawing like a very extended line here. Like, let me, yeah, show. So it should be like way over here and tiny, tiny, tiny. And it's like over here. And there's my 17 that I popped in with on this sample. And of course, this looks ridiculous. So this sample is so far away from the mean that it is highly unlikely. So the probability of this happening is so small that the book just said it's 0. In fact, if you try to do a calculation like on a computer, because there is ways of calculating on the computer, it'll probably say 0. All right, it is just going to be so small. So here's what we then think then, because that sample is so unlikely to occur, we believe that the problem is the original statement that we based this all on, and that is that the population mean is 15. That's the thing that's probably wrong. So, since our p-value is so small, we're going to conclude that this sample is too rare. This is not how we're going to always write this. We're going to formalize this in a second. This sample is too rare, so we're going to conclude that the null hypothesis is wrong. So we're going to reject the null hypothesis. So we're just kind of trying to talk about what the p-value is in this scenario. So the p-value is the probability of this happening. That is the p-value. And the book basically said that the p-value is 0. So it's so unlikely to happen that it practically is impossible. All right. So we would reject the null. All right, let's kind of get more into this in a little bit more of a formal terminology. Now, I mentioned that we're interested in minimizing type 1 error. So often we will have an amount that we're okay with the type 1 error being. In other words, maybe you're okay if you have a chance of that error occurring and it's 10%. Or maybe you're really worried about making a type 1 error, so you want it to be very low, like 1%. So we will use the type 1 error alpha to help us write conclusions based on the p-value. So if our p-value is smaller than alpha, we're going to reject the null. If our p-value is bigger than alpha, we will not reject the null. So remember, the p-value is the probability that our sample occurs based on the assumptions made. So let's look at an example where we kind of pull this in. Oops, I'm sorry. Of course, it jumped really far back. I apologize. Okay, where we pull this in and we kind of use this terminology and language to help us. So genetics lab claims their procedures improve the chances of a boy being born. So to improve the chance of a boy being born, we're assuming that the chance at the moment is a 50-50 chance. We know that that's not really true, but just for the moment, we're saying that maybe it's a boy, maybe it's a girl, 50-50. Okay. So they created a hypothesis test that said that the proportion of boys is 50%. And they are claiming that they are improving that it's greater than 50%, the chance that you'll have a boy. Now, for them, they're keeping their type 1 error very low. And therefore, the p-value, which is the probability of their sample occurring, is pretty low too. It's only a 2.5% chance their sample is going to occur. So they looked at a bunch of births and they measured their proportion, okay? But here's the problem. Based on the fact that they want their type 1 error so low, I'm seeing that the p-value, wow, I forgot the dash. P-value is of 0.25 is bigger than alpha of 0.01, I'm sorry. Therefore, we won't reject the null. I'm going to use these 3 little dots to mean therefore. That's the science notation of therefore. So do not reject the null. What that means is we don't have enough evidence to say that the lab improves the chances of a boy being born. Now, that doesn't mean they can't collect more evidence, and maybe they would be able to say that they do have enough evidence that there is a greater than 50% chance of a boy being born. Okay. But at the moment, because they chose their alpha value to be so small, and our p value happens to be a little bit bigger than that, even though it's a low probability of occurring, it's still not small enough. So we wanted to come up with a sample that was so rare, so small of a chance of occurring that we were like, haha, our original assumption that p equals zero point 0.5 is completely wrong. That's just absolutely wrong, and we can throw that out. And therefore we're correct. Our proportion is in fact greater than 50%.